NASA's James Webb Space Telescope has only just begun its mission, but it has already revealed cosmic riddles. Among these mysteries is Oumuamua, the first known interstellar visitor to our solar system. As the James Webb Space Telescope captures its first true image, could Oumuamua's origin point to extraterrestrial life? What might this revelation imply for humanity's understanding of the universe? Join us as we uncover the startling secrets of Oumuamua, which may challenge everything we thought we knew about the cosmos. Oumuamua, the first known interstellar object to pass through our solar system, captivated the world in 2017. Unlike anything previously observed, the Pan-STARRS Observatory identified this object, sparking intense scientific debate and challenging established theories. This mysterious visitor raised more questions than answers, with its peculiarities only adding to the enigma surrounding its source and nature. The fact that Oumuamua's origin is still unknown adds another layer of intrigue. Although it entered our solar system from the direction of the Lyra constellation, the exact location of its parent star system remains unclear. The object's incredible speed, relative to the Sun, suggests that it is highly unlikely to have originated within our solar system. Instead, it may have been traveling through the galaxy for millions, if not billions, of years before reaching us. The exact flight path and origin of Oumuamua are still unknown, as the stars it may have passed near have since shifted from their original positions, making it difficult to pinpoint its stellar home. Additionally, the object's approach from above the ecliptic plane, the approximate plane in which most planets and interstellar objects revolve, further complicates the situation. Due to its odd trajectory, Oumuamua didn't come into close contact with any of our solar system's main planets, leading scientists to speculate that its journey through space was largely unobstructed. Researchers have tried to trace Oumuamua's path using data from the European Space Agency's Gaia spacecraft, suggesting that it may have come from one of several nearby star systems. These potential origins include the red dwarf star H3757, the Sun-like star HD 29224, and two other stars with less familiar names. However, despite these efforts, the object's exact origin remains a mystery. Another puzzle lies in its physical appearance. While various artistic representations have been created, no definitive image exists of what Oumuamua looks like. Observations suggest that it is elongated, approximately 10 times longer than it is wide, an exceedingly rare shape compared to other interstellar objects, as most comets and asteroids have a length-to-width ratio of about 1:3. Oumuamua's brightness changed by a factor of 10 every 8 hours, indicating significant elongation and rapid tumbling. As it traveled through space, this tumbling made it appear as though it was flashing. Unfortunately, because the object was visible for such a short time, scientists have not yet been able to capture a detailed image of it, adding to its mystery. To further deepen the intrigue, Oumuamua experienced unexpected acceleration as it neared the Sun. Observations from the Hubble Space Telescope and other ground-based observatories showed that its speed increased slightly, altering its expected trajectory. This acceleration could be explained by outgassing, a phenomenon where gas and dust are released from an object's surface, which is commonly observed with comets. However, no direct evidence of outgassing was detected with Oumuamua. Some scientists speculate that the acceleration might have been caused by gas jets or the sublimation of frozen materials such as solid hydrogen or nitrogen ice. These theories remain speculative, given the lack of concrete evidence. Despite its brief journey through our solar system, Oumuamua is now speeding away at approximately 26 kilometers per second. The object is expected to exit our solar system in about 20,000 years, a mere blink in galactic terms. The short observation window and the object's rapid velocity make it challenging to study further. Voyager 1, the fastest spacecraft ever launched, travels at 16.6 kilometers per second, making it implausible for us to catch up to Oumuamua with current technology. Even advanced concepts like laser propulsion and solar sails would struggle to reach the speeds needed. The peculiar characteristics of Oumuamua have sparked numerous theories regarding its origins. One possibility is that Oumuamua is a fragment of a larger celestial body, such as a planet or moon, that was ejected from its host star system during a near collision with another star. This theory suggests that Oumuamua may have been drifting through interstellar space for millions or even billions of years before crossing paths with our solar system. Another theory proposes that Oumuamua may have been part of a larger object that was torn apart by tidal forces as it passed close to a star, which could explain its elongated shape. Avi Loeb, an astrophysicist, has put forward a more unconventional hypothesis: Oumuamua could be a form of alien technology. Loeb has suggested that the object's unusual shape and behavior might be better explained by an artificial origin, speculating that Oumuamua could be a solar sail or a fragment of a Dyson sphere, a hypothetical structure designed to harness energy from a star. Such an object would require advanced technology to construct, challenging our current understanding of natural celestial bodies. The mystery of Oumuamua continues to captivate scientists and scholars alike. Discovered in October 2017, this interstellar visitor has become a subject of intense debate in the astronomical community due to its strange characteristics. With each new observation, fresh questions arise about its composition, structure, and the possibility of a technological origin. As scientists attempt to unravel the nature of Oumuamua, they are faced with numerous possibilities. If the object's composition differs from anything found in nature, it may suggest that Oumuamua is not a typical celestial body. For instance, if its structure resembles that of a spacecraft, it would imply a level of sophistication far beyond a simple rock or asteroid. To truly understand Oumuamua, detailed information is needed, especially if there are any technological traces. Avi Loeb, a leading expert in the field, has argued that catching up to Oumuamua with a spacecraft is a formidable challenge. The object's tremendous speed, estimated at 315,000 km per hour, 196,000 miles per hour, combined with its trajectory, makes interception extremely difficult with current technology. Despite these challenges, various mission proposals have been put forward to approach Oumuamua. These concepts aim to address the significant obstacles of high-speed travel and precise navigation. Existing chemical rockets are insufficient to achieve the speeds necessary to overtake Oumuamua, but innovative methods could potentially be employed to reach it. One such method involves using gravitational slingshots or flybys. This technique, also known as a gravity assist or the abirth maneuver, relies on the gravitational pull of large celestial bodies such as the Sun or Jupiter to boost the speed of a spacecraft. By flying close to these massive objects and utilizing their gravity, spacecraft can accelerate significantly. This technique has been successfully used in past missions, such as the Voyager probes, to propel them toward the outer planets. Adam Hibberd, a freelance software developer based in the United Kingdom, has been developing potential missions to reach Oumuamua using his expertise in trajectory optimization. After hearing about the discovery of Oumuamua, Hibberd began working on flight plans for a mission to intercept the object. Hibberd and his Project Lyra team have proposed several mission designs, one of which involves launching a spacecraft in 2030 that could potentially reach Oumuamua in about 22 years. Initially, the team considered missions that would involve close encounters with the Sun, which would require significant shielding to protect the spacecraft from extreme heat. However, this approach would severely limit the payload capacity. As a result, Hibberd and his colleagues began exploring alternative strategies that would avoid close solar flybys, instead relying on Jupiter's gravitational pull. The team identified two potential paths to reach Jupiter from Earth, both involving a series of slingshot maneuvers around the inner planets. These approaches would allow the spacecraft to gain enough velocity to use Jupiter's gravity to slingshot toward Oumuamua. These strategies would result in a mission duration of around 31 years, 9 years longer than trajectories that involve close solar flybys. Marshall Eubanks, the chief scientist at Space Initiatives Incorporated and a member of Project Lyra, is enthusiastic about sending a spacecraft to Oumuamua or other interstellar objects. He points out that while missions to nearby stars are being proposed, Oumuamua remains a far more accessible target. Even after a century, Oumuamua will be about 150 astronomical units away, compared to Proxima Centauri's 4.24 light-years, making it a much closer target for exploration. Catching up to Oumuamua is technically feasible with current technologies, such as SpaceX's Falcon Heavy. However, crossing the vast distances involved and accurately locating the object presents significant challenges. Oumuamua's current position is highly uncertain, making its precise location difficult to determine. Finding an object as small as Oumuamua in the vast darkness of space is a challenge, particularly given that its distance is uncertain, comparable to the distance between Earth and the Moon. One potential solution would be to send a scout mission to locate Oumuamua before dispatching a larger spacecraft for closer inspection. This preliminary mission could use a large telescope, possibly half the size of the Hubble Space Telescope, to search the sky for the object. Alternatively, a swarm of tiny spacecraft could be deployed to survey a vast area. The Breakthrough Starshot project is exploring this idea, aiming to develop technology to send swarms of small, laser-propelled probes to nearby star systems. These tiny spacecraft could theoretically reach Oumuamua within a few years, providing critical information about its location and properties. Even if these scout probes were to find Oumuamua and relay its location, they would offer valuable data on whether the object continues to show non-gravitational acceleration, which would indicate persistent forces beyond gravity. Such information would be essential for planning future missions to explore Oumuamua more closely. Any subsequent mission would require a significant commitment. Missions similar in scale to NASA's New Horizons, which investigated Pluto and continues to explore the Kuiper Belt, could cost around $1 billion. Securing this kind of funding may be difficult due to uncertainties and the possibility that the mission may discover very mundane objects. Despite these challenges, there is still hope for future opportunities. The European Space Agency's Comet Interceptor mission, scheduled to launch in 2029, is an example of a fully funded and approved mission that could be prepared for future interstellar targets. The Comet Interceptor will consist of one large spacecraft and two smaller probes, which will travel to the Earth-Sun system's L2 Lagrange point. From there, they will await the discovery of a new interstellar object or a pristine comet from the outer solar system. The mission will conduct flybys to capture photos, spectra, and other data, offering insights into objects similar to Oumuamua. The Comet Interceptor is equipped with 3 cameras, one on the main craft and one on each of the smaller probes, to provide 3D views as the spacecraft approaches its target. The mission will also employ infrared imaging and a mass spectrometer to analyze any gases emitted by the comet. The larger craft plans to pass within 1,000 kilometers of its target, while the smaller probes will come even closer, at approximately 850 and 400 kilometers, respectively. The mission has a 5-year window to locate and study its target, offering an exciting opportunity to learn more about interstellar objects. The diversity of known interstellar objects, such as Oumuamua and Comet Borisov, presents an opportunity for valuable scientific discoveries. Observing and comparing these objects could provide substantial insights into their composition. The exact makeup of an interstellar object like Oumuamua is still unknown, but its distinctive shape may help scientists better understand its origin, whether natural or artificial. Its elongated, cylindrical shape has led to speculation about its potential as a manufactured object rather than a typical rock. Observations of changes in brightness, similar to those seen with Oumuamua, have fueled discussions that it may resemble a spacecraft rather than a natural object. Detailed inspection and study are essential, especially if there are signs that the object may contain advanced technology. Tracking Oumuamua poses significant challenges due to its high speed, nearly 20 km per second, which is too fast for current chemical rockets. However, gravity assist techniques may provide a viable alternative. Adam Hibberd, an independent software engineer from the UK, has been working on trajectory optimization for interplanetary missions. When Oumuamua was first discovered, he began using his software to simulate potential missions to the object. He joined Project Lyra, a team dedicated to creating credible flight plans to reach Oumuamua. One proposed mission would begin in 2030 and take around 22 years to reach the object. To overcome these challenges, Hibberd and the Project Lyra team explored other options that utilize Jupiter's gravity instead of the Sun's. 2 potential trajectories involve repeated gravity assists from the inner planets to approach Jupiter, followed by a gravity assist from Jupiter to accelerate the spacecraft toward Oumuamua. These paths would take about 31 years and offer a viable alternative to the sun-centric approach. Marshall Eubanks, chief scientist at Space Initiatives Incorporated and a member of Project Lyra, believes that a mission to Oumuamua is inevitable, given the growing interest in sending missions to nearby star systems. Even though Proxima Centauri is approximately 4 light-years away, Oumuamua will still be relatively close in a century, making it a more feasible target for exploration than distant stars. A return mission to Oumuamua would likely require a larger spacecraft, similar to NASA's New Horizons, which investigated Pluto and is now exploring the Kuiper Belt. Such missions, which cost around $1 billion, face funding challenges, as well as the risk of missing the target or discovering it to be an ordinary rock. Another intriguing concept is the von Neumann probe, named after mathematician John von Neumann. These self-replicating probes could explore space autonomously, creating copies of themselves using local resources. They could travel across the galaxy, collecting data and potentially preparing planets for colonization. However, the absence of observed von Neumann probes raises questions about their feasibility and why advanced civilizations might avoid developing them. The Matryoshka brane is another speculative idea that expands on the Dyson sphere concept, proposing a stacked structure of many Dyson spheres, each absorbing energy from the layer beneath it. This massive computational network could simulate entire universes or perform incredibly complex calculations. The theory relates to the simulation hypothesis, which suggests that our universe could be a simulated reality created by an advanced civilization. Building a Matryoshka brane would require immense engineering and material resources, presenting significant challenges. Recently, the James Webb Space Telescope made a groundbreaking discovery, revealing a crucial building block of life from the early universe. This discovery challenges our previous understanding of the origins of the first galaxies. The telescope detected carbon in a compact galaxy just 350 million years after the Big Bang, making it the oldest detection of an element other than hydrogen. This finding, which has been accepted for publication in Astronomy and Astrophysics contradicts earlier theories that predicted carbon would not form in significant amounts until around 1 billion years after the Big Bang. Roberto Maiolino, a co-author and professor of experimental astrophysics at Cavendish Laboratory, remarked on carbon's surprisingly early appearance, suggesting that it could be the universe's oldest metal. Previously, it was believed that elements heavier than hydrogen and helium, collectively called metals in astronomy, were formed in stars and dispersed through supernova explosions. This process, thought to require several star life cycles, seems to have occurred much more rapidly than previously believed. The discovery was made in the distant galaxy GSA-2, which is significantly less massive than the Milky Way, and signs of carbon, oxygen, and neon were detected. This suggests that carbon production may have taken place in less massive stars than previously assumed, allowing carbon to escape and spread across the universe earlier than expected. The implications of this discovery are profound. It suggests that the universe could have been hospitable to life much earlier than we thought. If carbon formed that early, it is possible that life, or at least the basic building blocks of life, could have emerged far sooner than anticipated. This opens the possibility that life in the universe might not be limited to forms resembling those on Earth. Instead, extraterrestrial life might be based on entirely different materials or structures, such as crystalline or metallic forms, making it more challenging to detect with current technology. This finding brings to mind the Fermi paradox, which highlights the contradiction between the high probability of extraterrestrial civilizations and the lack of evidence or interaction with them. Despite our increasing efforts to search for life and the discovery of thousands of exoplanets, we have yet to find conclusive evidence of extraterrestrial life, whether intelligent or microbial. Although there are many planets that could potentially support life, the silence we encounter in our search underscores the absence of detectable life. In 1961, Frank Drake proposed the Drake equation, one of the most famous methods for estimating the probability of finding extraterrestrial civilizations. The equation breaks down the problem into various factors to calculate the likelihood of detecting intelligent extraterrestrial life. It begins with the average rate of star formation in our galaxy, which, despite ongoing research, is estimated to be around 1.5 stars per year. Although this number seems small, it adds up over the vast timescales of the universe, contributing to the overall likelihood of life-bearing planets. The Drake equation is a mathematical model that considers several factors, including the fraction of stars with planets, the number of planets capable of supporting life, and the proportion of those planets where life can thrive. The algorithm also investigates the proportion of planets with life that support intelligent civilizations capable of technological advancement. On Earth, only one species has developed such intelligence among countless others, implying that intelligent life may be uncommon. The equation also examines how many advanced civilizations send detectable signals, such as radio transmissions or other forms of communication. The absence of responses from potential extraterrestrial civilizations raises questions about their existence and willingness to cooperate. The equation concludes by considering the longevity of civilizations, as long-lasting civilizations are easier to identify than those that quickly self-destruct. SEI has employed various approaches to search for signals from alien civilizations, including the use of radio telescopes such as the Very Large Array, VLA, and the Green Bank Telescope. Despite decades of research, no definitive evidence has been found. As new technologies and methodologies emerge, the chances of uncovering evidence of life or advanced civilizations may increase. The formation of new stars, which stretches far into the future, presents intriguing possibilities for the presence of life throughout the universe. According to projections, new stars could form and sustain life for another 100 quadrillion years. However, gravitational interactions are expected to gradually erase galaxies from our observable reality. Despite the vastness of the universe, the quest for life beyond Earth remains a fascinating and ongoing endeavor. Currently, Earth is the only known location where life has developed and continues to thrive. Yet, the vastness of the universe offers numerous opportunities for life to exist elsewhere. Several exoplanets have been identified as potential candidates for life or human settlement. One of the most promising of these exoplanets is Kepler-186f, discovered in April 2014. Located approximately 490 light-years from Earth, Kepler-186f is one of the most Earth-like planets found to date. It lies within the habitable zone of its host star, a red dwarf, and is only about 10% larger than Earth. Though reaching Kepler-186f with current technology would take hundreds of millions of years, its discovery marks an important step in the search for habitable planets. Another exciting world is Kepler-283c, discovered from data obtained by the Kepler Satellite Observatory. Kepler-283c, almost twice the size of Earth, orbits its star much closer than Earth does to the Sun. Located more than 1,700 light-years away, Kepler-283c is on the verge of supporting Earth-like life as it resides in its star's habitable zone. The GJ667 system, located just 22.1 light-years away, offers two intriguing planets, GJ667cc and GJ667ce. This triple-star system presents a unique opportunity, as both planets lie within their stars' habitable zones and offer the rare possibility of viewing three suns from their surfaces. Though relatively close in astronomical terms, visiting these planets would still pose a significant challenge. However, they provide valuable insights into the types of habitats that may exist elsewhere in the galaxy. Other notable findings from NASA's Kepler Space Telescope include Kepler-62e and Kepler-62f, located around 100 light-years away in the constellation Lyra. These planets, part of a system that may contain water worlds, are about 1.6 and 1.4 times the size of Earth, respectively. Both planets orbit a red dwarf star, with Kepler-62e completing its orbit in 122 days and Kepler-62f in 267 days. These worlds could be covered entirely in liquid water, offering fascinating opportunities for life, possibly including vast marine habitats. Another interesting exoplanet is GJ581d, located about 20 light-years from Earth. While its close proximity is notable, GJ581d's atmosphere, rich in carbon dioxide, could make it hostile to human life, which requires oxygen to survive. However, its rocky composition and the presence of liquid water suggest the potential for lush rainforests or other unusual habitats. The James Webb Space Telescope, JWST, launched in late 2021, is at the forefront of exoplanet research and the search for extraterrestrial life. It is currently observing the TRAPPIST-1 system, which consists of 7 Earth-sized planets, 3 of which are located within the habitable zone of their star. The JWST represents a major advancement in our ability to gather and analyze light from other planets, bringing us closer to answering the age-old question of whether we are alone in the universe. The expansion of the cosmos, first observed by Edwin Hubble nearly a century ago, is fundamental to our understanding of cosmology. The Hubble constant, which represents the universe's rate of expansion, has been the subject of extensive research and debate. Recent data from the James Webb Space Telescope suggest that our current understanding of the cosmos may need a significant revision. The difference in the rate of expansion, known as the Hubble tension, has revealed that our picture of the universe may be incomplete. The standard cosmological model, known as lambda cold dark matter, CDM, assumes that the universe's expansion rate is uniform and predictable. According to this model, the universe began with the Big Bang, which triggered a period of rapid inflation during which the universe expanded like a balloon. As the cosmos cooled, matter began to cluster together, forming the first galaxies connected by a vast cosmic web. However, the introduction of dark energy, a mysterious force that accelerates the expansion of the universe, has complicated this picture. Einstein proposed dark energy as a cosmological constant, accounting for about 70% of the universe's energy density. It is thought to have a constant energy density embedded within the fabric of space-time. Despite its importance, dark energy remains poorly understood. Cold dark matter makes up another 25% of the universe's energy density, while normal matter accounts for only 5%. The CDM model has successfully predicted many aspects of cosmic evolution, though it faces challenges due to the Hubble tension. Observations of the cosmic microwave background, CMB, remnant of the early universe, have yielded a Hubble constant of around 67 km per second per megaparsec. This figure represents how quickly galaxies are receding from us based on their distance. However, observations using other methods, such as nearby supernovae and galaxy cluster expansion, suggest a faster rate of expansion. As the universe expands, galaxies located more than 4,475 megaparsecs away from us are receding faster than the speed of light. Astronomers use several methods to determine the universe's expansion rate, one of which involves pulsating stars called Cepheid variables. These stars have helium-rich outer layers that pulsate as they absorb and release radiation, causing their brightness to vary periodically. Cepheid variables behave like distant signal lamps due to these pulsations. In 1911, Henrietta Swan Leavitt made a groundbreaking discovery when she observed that the intrinsic brightness of a Cepheid is directly related to its pulsation period. The slower a Cepheid pulsates, the brighter it is. This discovery allowed astronomers to calculate the absolute brightness of a Cepheid and thus determine its distance from Earth. This method revolutionized our understanding of cosmic distances and transformed Cepheids into reliable standard candles for measuring the scale of the universe. By combining Cepheid data, astronomers can construct a cosmic distance ladder, with each rung representing a different method of distance measurement. Measuring nearby Cepheids and verifying their distances using geometric methods forms the first step of this ladder. SEI readings provide subsequent rungs. Afterward, astronomers measure distances to stars and supernovae on each rung and examine how much the expansion of the universe has redshifted their light. This approach enables a precise calculation of the Hubble constant, allowing for the measurement of the universe's expansion rate. In 2019, a notable measurement was obtained using the Hubble Space Telescope to observe the Large Magellanic Cloud, one of the Milky Way's nearest neighbors. The result was a relatively high expansion rate of 74 km per second per megaparsec, significantly different from measurements made by the Planck satellite. This discrepancy has led to what is now known as the Hubble tension. The cause of this disagreement remains unknown. Some researchers speculate that new physics may be needed to resolve the discrepancy. A measurement error on the lowest rung of the cosmic distance ladder could explain the observed variations in Cepheids. These stars exhibit consistent brightness variations, and their period-luminosity relationship allows for precise distance calculations. However, measuring Cepheid variables in distant galaxies is difficult because they are hard to distinguish from other stars and interstellar dust. Recent observations from the James Webb Space Telescope have improved the accuracy of distance measurements using Type Ia supernovae, which occur in even more distant galaxies. Nonetheless, the persistent Hubble tension suggests that there may be fundamental gaps in our understanding of the universe. According to some astronomers, Earth may be located near a supervoid, a vast region of space with a lower-than-average density that spans approximately 2 billion light-years in diameter. Galaxies within this supervoid may migrate outward toward its edges, which could impact estimates of the universe's expansion rate. Researchers have turned to modified Newtonian dynamics, MOND, an alternative theory of gravity proposed to explain galaxy activity without referencing dark matter, to help account for the supervoid. However, MOND struggles to describe large cosmic structures, leading to the introduction of a new particle known as sterile neutrinos. These neutrinos are a form of dark matter, and their combination with MOND might explain the supervoid and resolve the Hubble tension. Ironically, MOND was originally suggested as a way to eliminate the need for dark matter, but now it embraces it to solve this discrepancy. Some astronomers continue to question the validity of MOND as a hypothesis for understanding cosmic events. While MOND is an interesting alternative to dark matter, it has faced significant criticism. Most astronomers and cosmologists doubt its effectiveness, particularly because it still requires some form of dark matter to account for the diversity of structures found in the universe. The concept of sterile neutrinos, proposed to support MOND, remains theoretical and lacks sufficient evidence. Additionally, for MOND to be credible, the Milky Way would have to be located near the center of a local supervoid, a coincidence that is difficult to reconcile with any credible cosmological model. Despite these challenges, research into MOND and related ideas may provide valuable insights and could potentially alleviate the ongoing Hubble conflict. Current findings are based on relatively simple models of cosmic structure formation, and further progress will require more advanced simulations. Ultimately, empirical evidence will be necessary to determine the validity of these models. Turning to recent astronomical milestones, NASA recently celebrated the second anniversary of the James Webb Space Telescope, JWST. The first significant announcement occurred on July 11, 2022, when President Biden and Vice President Harris revealed JWST's initial image during a White House press conference. This photograph, known as the Deep Field, showcased the galaxy cluster SMACS 0723. The following day, NASA released additional breathtaking images, including Stephan's quintet, the cosmic cliffs of the Carina Nebula, and the remnants of a supernova from a dying star. Since then, the JWST has continued to deliver stunning photos and transformative data, greatly enhancing our understanding of the universe. The telescope has discovered some of the most distant galaxies ever observed, including those that existed when the universe was only 300 million years old. Moreover, the JWST has uncovered quasars powered by supermassive black holes that formed less than a billion years after the Big Bang, raising questions about how these cosmic giants grew so quickly in the early universe. JWST's ability to detect light stretched by cosmic expansion allows it to observe early galaxies and quasars, making it a critical tool for understanding the universe's beginnings. Surprisingly, the telescope has also proven valuable for studying objects within our solar system, despite initial concerns that proximity might hinder observations. JWST has provided unprecedented views of familiar solar system worlds like Jupiter. To commemorate the second anniversary of JWST's operation, NASA shared another stunning image, this time depicting ARP-142, a view of two colliding galaxies that resemble a penguin and an egg. These galaxies, located around 326 million light-years from Earth in the constellation Hydra, had been seen before, but never in such detail. The infrared image captured by JWST's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, reveals intricate details of their interaction and structure. The penguin shape is created by the twisted spiral galaxy NGC 2936, while the egg shape is the elliptical galaxy NGC 2937. The interaction between these galaxies began 25 to 75 million years ago, causing significant disruptions in star formation in NGC 2936. The photograph also includes more distant galaxies, adding depth and context to the cosmic scene. In addition, JWST recently witnessed a remarkable event involving a supermassive black hole and two satellite galaxies. This discovery sheds light on the early universe by revealing a quasar located less than a billion years after the Big Bang. The quasar, PJ30821, is powered by a supermassive black hole with a mass of 2 billion suns. The galaxies involved in this interaction are highly evolved, which is surprising given their young cosmic age. The merging of these galaxies is expected to funnel a large amount of gas and dust into the black hole, enabling it to grow and sustain the quasar's brilliance. Quasars, which form when supermassive black holes accumulate surrounding matter, are known for their extreme luminosity, often outshining all the stars in their host galaxies. This luminosity provides crucial information about the age and evolution of quasars. JWST's data reveals that black holes in high-redshift quasars, as well as their host galaxies, grew rapidly and efficiently in the early universe. This discovery challenges existing models and prompts further research into the conditions that allowed for such rapid growth. JWST's findings are helping scientists understand how galaxies and supermassive black holes formed in the early cosmos. Studying these early cosmic objects offers vital insights into the origins and evolution of structures in the universe. The study of early quasars and their host galaxies also helps explain the processes that led to the diverse cosmic landscape we see today. The quasar photoionization process is also occurring in a second satellite galaxy, but this time it is driven by a burst of rapid star formation. This second galaxy is distinct from the first and the active galactic nucleus, AGN, in that it appears to be metal-poor. Federica Lono, an astrophysicist and team member, explained that the improved capabilities of JWST's NIR-SPEC instrument made this discovery possible. For the first time, researchers can study a rich optical band of emission lines, as well as diagnostic data on the gas properties near the black hole in the quasar-hosting galaxy and its surrounding satellites. This analysis includes measuring the emission of hydrogen atoms and comparing the chemical elements produced by stars, which helps determine the metal content of the gas. As light travels from this early universe quasar across a wide range of the electromagnetic spectrum, including optical light and X-rays, it shifts into the infrared after more than 12 billion years due to cosmic expansion. This phenomenon, known as redshift and denoted by Z in astronomical studies, occurs when the universe expands, stretching the wavelengths of light. Thanks to its infrared sensitivity, JWST excels at observing high redshift, high Z objects like PJ3821, allowing it to analyze the spectra of quasars and their companion galaxies with unprecedented precision. JWST's sensitivity in both the near and mid-infrared ranges is critical for monitoring these distant cosmic events. In another major discovery, JWST has captured images of a spectacular cosmic ring created by gravitational lensing. This image features RxJ 1131231, a distant quasar located roughly 6 billion light-years from Earth. The gravitational field of a foreground elliptical galaxy distorts the light from the quasar, producing a bright arc and multiple images of the object. This effect, which resembles jewels arranged in a ring, occurs because the elliptical galaxy acts as a natural lens, magnifying the quasar's light. The new image, captured by JWST's mid-infrared instrument, MIRI, is part of a broader study of dark matter and its distribution. RxJ 1131231 is considered one of the best examples of lensed quasars observed so far, based on current and previous observations from other telescopes. In another area of exploration, Mercury, the closest planet to the Sun, presents new challenges to previous conceptions of its harsh and barren environment. Despite its proximity to the Sun and the intense solar radiation it receives, Mercury remains a planet of contrasts. Its day and night sides experience temperature differences of around 600 degrees Celsius. Yet recent measurements indicate that Mercury has a more dynamic environment than previously thought, with a thin atmosphere, a magnetic field, and volatile substances typically associated with larger and more distant planets. Recent large telescope studies have revealed unexpected anomalies about Mercury that challenge earlier theories. The planet is predominantly composed of metal, with a thin rocky outer layer. The key question remains, why does Mercury have such a different composition compared to the other planets in our solar system? Scientists are currently attempting to unravel various riddles concerning Mercury. Mercury's high orbital velocity around the Sun, which averages 36 million miles, and its orbit, which spans from 29 to 43 million miles, contribute significantly to its distinctive features. The planet orbits the Sun at an average speed of around 29 miles per second, completing each orbit in just 88 Earth days. Despite its modest size, with a diameter of approximately 3,332 miles at the equator, making it only slightly larger than Earth's moon, Mercury's rapid orbit makes it difficult to observe. The planet is also noted for its uncommon transits, where it passes between Earth and the Sun approximately 13 times every century. During these transits, observers on Earth can witness Mercury moving across the Sun's disk. Additionally, due to its position within the solar system, Mercury experiences retrograde motion 3 to 4 times a year, creating an optical illusion in which it appears to move backward in the sky relative to other planets. If viewed from Mercury's surface, one would witness a peculiar phenomenon where the Sun seems to rise, set, and then rise again within the same day. This happens when Mercury's orbital speed surpasses its rotational speed. Mercury formed around 4.5 billion years ago from the dust and gas surrounding the young Sun. The planet cooled rapidly, contracting within the first billion years, which prevented significant volcanic activity. Despite its small size, Mercury is incredibly dense, with an iron core accounting for over 60% of the planet's volume, compared to Earth's core, which makes up only about 15% of its volume. This high density suggests Mercury has a unique formation history. According to some theories, early solar winds or a massive impact may have stripped away much of Mercury's outer shell, leaving behind only its dense core. In 1973, the Mariner 10 mission detected Mercury's magnetic field, which surprised scientists. It was assumed that a small planet like Mercury would have cooled too quickly to maintain such a field. Nevertheless, Mercury still possesses a magnetic field, although it is much weaker than Earth's. Mercury, the closest planet to the Sun, endures some of the most extreme temperatures in the solar system. It completes its orbit around the Sun in just 88 Earth days, making it the fastest planet. However, its night side experiences frigid temperatures of about -173 degrees Celsius -280 degrees Fahrenheit, much colder than any natural temperatures on Earth. By comparison, Venus, which is twice as far from the Sun as Mercury, has an average temperature of around 462 degrees Celsius 864 degrees Fahrenheit and takes roughly 225 Earth days to orbit the Sun. Venus's slow rotation results in prolonged periods of daylight and darkness. The difference in atmospheric conditions between Venus and Mercury accounts for their contrasting temperatures. Venus has a dense atmosphere composed mainly of carbon dioxide, with pressure almost 90 times greater than Earth's, while Mercury has a much thinner exosphere instead of a substantial atmosphere. Mercury's exosphere is so thin that its pressure barely registers, and as a result, the planet cannot retain heat the way Venus does. Mercury's exosphere is periodically replenished by gases released from the planet's surface, solar particles, and meteorite impacts. The exosphere consists of atomic sodium, potassium, and calcium. While these elements are not typically considered gases, they are present in Mercury's exosphere due to solar winds and meteor impacts. Earth-based observatories have detected these metallic elements, which create a faint shimmering tail extending up to 15 million kilometers behind Mercury. This tail's length varies depending on the planet's distance from the Sun. At certain times of the year, the tail may appear as a faint orange glow in Mercury's sky, resembling the glow of sodium street lights. Although Mercury's extreme temperatures and lack of a substantial atmosphere suggest the absence of water, radar scans from the 1990s, conducted by the Goldstone Deep Space Communications Complex in California and the Arecibo Observatory in Puerto Rico, revealed two brightly reflective patches near Mercury's poles. In 2012, the Messenger spacecraft found frozen water beneath a layer of carbon-rich material at Mercury's North Pole. The water remains stable in these permanently shadowed craters, where the temperatures are low enough for ice to persist over geological timescales. Messenger also detected other volatile elements on Mercury, including sulfur, potassium, and chloride. Volatiles are compounds that can easily shift between solid and gas states with temperature changes, and their discovery on Mercury raises intriguing questions about their origins and longevity. Mercury is also famous for its chaotic terrains, which are twisted ridges resembling a jumble of Jenga blocks. Some scientists believe these terrains were formed due to the loss of structural integrity caused by volatile release, while others suggest that they are the result of seismic waves generated by asteroid impacts on the opposite side of the planet. Mercury's surface also shows evidence of past volcanic activity. NASA's Messenger mission revealed that Mercury might have a 10-meter-thick diamond layer deep within the planet. These diamonds may play a role in heat transfer between Mercury's core and mantle, influencing its magnetic field. Understanding Mercury's unique geological features and diamond layer could shed light on planetary formation and evolution across the solar system. The European Space Agency's Bepicolombo mission has made significant strides in studying Mercury. This project, known for its innovative solar electric propulsion system, uses two 15-meter-long solar arrays to generate energy for its 4-ion thrusters. These thrusters use xenon propellant and are mounted on gimbals for precise control. BepiColombo consists of 3 spacecraft: the Mercury Transfer Module, which acts like a tugboat to transport 2 distinct orbiters to Mercury, the Mercury Planetary Orbiter, equipped with 11 scientific instruments to study Mercury's surface and surroundings, and the Mercury Magnetospheric Orbiter, built mainly by JAXA, which carries 5 sets of experiments. This spacecraft focuses on studying plasma and neutral particles from Mercury's magnetosphere and solar wind. While awaiting data from BepiColombo, scientists also rely on the James Webb Space Telescope, JWST, for insights. The JWST has several advantages over earlier missions. It boasts a large 21.7-foot mirror made of 18 gold-plated hexagonal segments, which allows it to capture more than 6 times the amount of light as the Hubble Space Telescope's 7.8-foot mirror. The JWST's superior light-gathering ability lets it record light from distant celestial objects 6 times faster than Hubble. The telescope's key innovation, however, lies in its ability to detect infrared light. The JWST can observe wavelengths from the red end of the visible spectrum to the mid-infrared range, while Hubble's optics are geared towards ultraviolet to near-infrared light, favoring visible light. Although the JWST's infrared resolution is not as sharp as Hubble's in optical light, its ability to observe distant galaxies and newly formed stars is groundbreaking. As the universe expands, ultraviolet and visible light from early objects shift to longer infrared wavelengths, making the JWST's infrared observations crucial for studying these young galaxies. The JWST's ability to observe infrared wavelengths also reveals details hidden by dust surrounding young stars. This capability extends to observing our solar system, where the JWST has already provided vital insights. Early studies have included monitoring cloud belts on gas and ice giants, analyzing cloud patterns on Saturn's moon Titan, exploring Pluto's atmosphere, and investigating smaller asteroids and trans-Neptunian objects. In September, the James Webb Space Telescope, JWST, notably observed the asteroid moonlet d'Oros, documenting the effects of NASA's Double Asteroid Redirection Test, DART, which significantly altered the object's orbit. This observation is crucial in helping NASA evaluate approaches for modifying the courses of potentially harmful asteroids. Among JWST's groundbreaking discoveries is the moon Ariel of Uranus. The telescope detected evidence suggesting Ariel may possess a subterranean liquid water ocean. Ariel's surface is covered with a substantial amount of carbon dioxide ice, which is unusual given its distance from the Sun, where carbon dioxide would typically convert to gas and escape into space. Previously, scientists hypothesized that radiolysis, the disintegration of chemicals caused by ionizing radiation from Uranus's magnetosphere, could be responsible for replenishing Ariel's CO2. However, JWST measurements now suggest that the carbon dioxide may originate from within Ariel, potentially from a hidden subterranean ocean. The research team used JWST to investigate Ariel's light spectra and compare them with lab simulations, discovering that Ariel contains some of the richest carbon dioxide deposits in the solar system. Additionally, for the first time, carbon monoxide was discovered on Ariel's surface. According to Richard Cartwright of the Johns Hopkins Applied Physics Laboratory, the presence of carbon monoxide, where surface temperatures are around -18 degrees Celsius, indicates active replenishment, as carbon monoxide is typically stable at much lower temperatures. While radiolysis may still contribute to carbon dioxide replenishment, the limited interactions of charged particles with Ariel's surface, particularly on its scarred side facing away from Uranus, could suggest active cryovolcanism, icy eruptions that release carbon compounds. The results also indicated the presence of carbonate minerals, which form when rock interacts with liquid water. This discovery further supports the possibility of a subterranean ocean on Ariel, a theory that future missions could help confirm. Despite only being visited once by Voyager 2 in 1986, Uranus and its moons remain a high priority for planetary scientists. The 2023 Planetary Science and Astrobiology Decadal Study emphasized the importance of a dedicated mission to Uranus and Neptune, the solar system's other ice giants. Such a mission could reveal critical information about these distant worlds and their moons, potentially confirming the existence of underground oceans. Insights from studying Uranus and its moons could also be applied to extrasolar planets, broadening our understanding of planetary systems beyond our solar system. JWST's recent discovery of a frigid exoplanet in the Epsilon Indi system highlights its potential. This exoplanet, known as EPS-InB, has a surface temperature of approximately 0 degrees Celsius, making it one of the coldest exoplanets yet observed outside our solar system. It orbits its red dwarf star at a distance similar to Neptune's orbit around the Sun, with each orbit lasting around 200 Earth years. Using its mid-infrared instrument, JWST observed EPS-InB, providing valuable characteristics that will help astronomers better understand the evolution of gas giant planets. This discovery also corrected previous estimates of the planet's mass and orbital parameters, revealing a highly elliptical orbit. The Epsilon Indi system comprises two brown dwarf companions, failed stars with insufficient mass for nuclear fusion. The peculiar architecture of this system, along with the frigid temperature of EPS-InB, sheds light on the formation and behavior of gas giants. JWST's ability to study this exoplanet and correct earlier errors demonstrates its revolutionary role in enhancing our understanding of planetary systems. As scientists continue to explore the depths of our solar system and beyond, advanced observatories like JWST become increasingly important. JWST's unique capabilities in infrared observation are poised to transform our understanding of distant galaxies, star formation, and planetary systems. What additional cosmic secrets will JWST uncover as it continues its mission to explore the universe?